Hi, my name is Andrew Buck. I'm from the University of Missouri, and today I'll be presenting our paper called Unreal Engine-Based Photorealistic Aerial Data Generation and Unit Testing of Artificial Intelligence Algorithms. So to begin, I want to talk a little bit about UAVs, or unmanned aerial vehicles. They make great research platforms, and they come in all sorts of shapes and sizes, from little drones that you can fly inside to really big ones that you can fly outside and put a lot of different sensors on. They're great because they can move freely in 3D space, and you can put a lot of sensors on them. You can put cameras, LiDARs, depth sensors of different types. And they're really great platforms for developing autonomous behaviors and studying how things move and can observe environments. There's a lot of applications that would benefit from having these drones be a little bit more autonomous, so giving them some sense of ability to control what they do on their own. So you can imagine applications like 3D scene reconstruction, surveillance, explosive hazard detection, search and rescue, and even just a little bit of autonomy could really help human operators in a lot of these situations. So our goal today is to develop a modular and extendable framework for studying UAV autonomy with photorealistic simulation tools. And why simulation? Real world data collection can be pretty challenging. It can be costly and time consuming. You risk losing your hardware if you crash, and there's usually not ground truth available directly. So you'd have to manually label objects. You don't have depth information precisely available to you. One of our previous papers discussed a platform that we tried to build from scratch to give us all of this autonomous control and a lot of capability. And there's a lot that goes into that. Meanwhile, simulation environments like Unreal Engine have matured to the point where we can produce really convincing looking photorealistic imagery and connect it to tools like AirSim and ROS to allow us to control a virtual drone and to export that imagery and listen for control feedback from real sensors. It's really compelling to use simulation to do a lot of this research now. And there's a huge marketplace of assets and maps that we can use to build up simulation environments, lots of diversity that we can create. It's a lot of times just easier to create a virtual environment than to go out and do a real data collection. So simulation is great. And so here is the architecture that we're proposing for studying this autonomous behavior. This is kind of a complicated diagram, but I'll go through it step by step here. We start in the top left. This is where we have our simulation environment. This is Unreal Engine running AirSim as a plugin. I'm going to go into each of these in a little more depth on the following slides. But this is able to produce a camera pose and color images. We can get segmentation, and in simulation we have access to the depth, which is not something that we would normally have on a real drone. We could estimate the depth, but we wouldn't have that accurate ground truth depth information. All of these observations get produced by the engine, and we use that then to construct a point cloud representation of the current observation. These can be done using ground truth, using that known depth, or we can estimate it using algorithms like epidepth, which we'll talk about in a little bit. And so these local point clouds get aggregated together into this voxel map server, or this database, this knowledge base of all of the observations and all of the information that we've observed up to this point in the map. And so this is really kind of the core representation of the agent's knowledge that it's going to use to decide how to do things and how to move in the environment and decide where to go. We'll talk about how we can evaluate all of that information and come up with different ways of looking at different features of that voxel space, and then using that, for instance, to do things like scoring, like figuring out how well it's doing, how well it's performing over time. And these feature maps also are used to pick goals and decide where we want to go. So we can define user preferences that weight different features of this space so that we end up producing different behaviors so that the drone prioritizes different things. So all of this comes back into a path planning and a waypoint controller module that decides, based on all of the information that's acquired so far and all of the inputs that we've given to it, what is the best place to go to and how should we get there? So what is the path to the next waypoint? This planning module then decides how it's going to tell the drone where to actually go, what to fly, if it needs to go to the next waypoint, where that waypoint should be. And there's always the option to override this control manually. So if a human operator wants to take control, or we detect a situation where we need to switch into a different behavior mode, that's always an option. So this is the overall framework, and now we're going to kind of go into each of these in a little more detail. So first of all, ROS, Unreal Engine and AirSim. ROS stands for Robot Operating System. It's essentially a message passing framework that allows us to have lots of independently distributed nodes in a network that communicate with one another. And so they're all talking to each other, doing their own computations and their own thing. And they communicate via some standard message types. So we can use some of the tools that are part of ROS to help visualize these messages and to understand what we're seeing. So images, point clouds, detections, and control commands can all be communicated with ROS. The Unreal Engine is the simulation framework that we're doing all of this simulation in. And so there's been a lot of development in this space where we can create very convincing photorealistic images and environments. And they're very easy to set up with a marketplace where we can purchase any content, maps, assets, vehicles, buildings, things that we want to put into an environment to test out. We can do that. And AirSim is a plugin that works with Unreal Engine to simulate a virtual drone. It lets us fly around in this virtual space, and it provides that pose, depth, and if we want to use the segmentation image, we can also have access to that. We can control that drone via ROS commands, and it's just a really nice way of virtualizing a drone. And all of the work now that we do in simulation can use AirSim and can use this ROS framework to transfer onto a real drone if we set that up. And so all of the infrastructure is in place. So the first step of our pipeline is to create a local point cloud representation of the current observation that the drone sees. And so we can do that with the images that we get, just the camera images and the pose and the depth map. We could also use a LiDAR sensor if we had that. So when we have the ground truth available to us, we can use that known depth and project that depth for every pixel in the image and get a dense point cloud that is exactly how far away things are from the drone in that current pose, that current moment in time. Now, it's not something that we can do on a real drone because we don't have access to that ground truth depth map, but we can estimate it. One of the algorithms we could use is EpiDepth. We have another paper on how that works in more detail, but essentially it uses just the camera images and the pose information to predict using stereo matching where how far away each of these pixels are. And so it produces an estimate of the depth that we can use. And we can use the ground truth now as a baseline to understand, how accurate is that reconstruction algorithm that we might actually be using on a real world drone. And so we can evaluate the accuracy in that way. So these local point clouds get aggregated into a larger map server. We might have a knowledge base that represents all of the information that the drone understands about the world. And we can store that in a voxel grid. So locations in this voxel grid might represent occupancy, it could represent features like color or some other measured quantity of the space. And we can use that then to decide where we want to go and understand what the free space and the spatial understanding of that scene actually looks like. So one tool that we can use is Octomap. Octomap is a probabilistic occupancy grid that uses octrees. It's part of ROS. And so we can use that as a way to aggregate all of our observations into a larger grid. And one of the nice things about Octomap is that it will actually represent the free space from the current camera position. So we can actually determine where a drone is able to go in that free space. Another option is to use OpenVDB. This is a library that's used for managing sparse voxel grids, often in the film industry. It's very efficient at managing very large voxel grids, and we can use that as well as an alternative. So once we have that voxel grid, we can decide how we want to process it. So lots of different ways that we can interpret that voxel map. For instance, we can get the elevation of the voxel map and use that as a basic path planning tool. So for instance, fly up to a certain height and avoid running into things that way. We can also do a little more complicated things, such as keeping track of how long it's been since a voxel has been observed. So measuring the age of a voxel. We can use it to compute the frontier of our observed space. So things near the edge of what we've observed are more interesting, perhaps. We can also have basic measurements, such as how far away is a location from where I am now, the drone distance or a target distance. So if we have a target object in this scene that says, hey, this is an item or an object of interest, how far away is it? So these are all different ways that we can evaluate what we understand about the environment. And then we can take all of those observations and use them to select where we want to go, our goal. And so one way to do that is with linear weights. So we might define manually what is our preference for each of these features that we observe. So maybe we want to prioritize age or frontier status so it explores more. Maybe we want to really prioritize the distance from the origin so it never leaves where it took off from. So we can define these weights, combine them in a linear weighting scheme to get a combined score. And then the maximum location in there, the location that has the highest value, then becomes the goal location. And so this gets updated as we get new observations. And so that location of the goal could change over time. And so that just represents the current moment in time. What is the most interesting place for you to explore? So once we have that location in mind, then we have to pass it to some type of path planning module that decides how is it going to get the drone from where it is now to that location. So maybe it uses just the elevation map, maybe it uses the free space of the octomap to plan a more complicated path. And so when it does that, then the path gets implemented with the controller. So that control then goes back to AirSim and actually flies the drone. And we can keep track of all this then with our scoring metrics. So we can track things like how many voxels have we observed in total in the map. Maybe we want to build up our observation space so we observe all of the map. We can keep track of the average age of voxels in that map so nothing gets too out of date. So we're always constantly looking at things. There's lots of things we could track in this, like how much battery the drone has, the number of collisions if it ever crashed. So there's lots of things that we can evaluate with this. Okay, so now I'm going to show you an example scenario. This is a loitering scenario where the objective is for the drone to simply map out its current location, the current environment. So it's going to take off here, and there's lots of different components that fit into this framework. And so here I'm just showing one set of windows that look into what's happening. So in the top left, we have the AirSim window that shows the drone running in the simulation. And the three sub windows there show the depth and the segmentation and the color image from the downward looking camera. That's what's being used to build up the point cloud. You can see in the top right, we have the two local point clouds being constructed. The gray is the ground truth, and then the one in color is our estimate being produced with EpiDepth. In the top middle, you have the elevation profile, and you can see now it's being sped up so that we don't have to wait for this whole thing to take place. But it's exploring where it wants to go. So down in the bottom middle, you see the combined score features, and that's being used to decide where the drone should go. The bottom right shows our voxel grid, where that little white sphere represents the current target location where it thinks it should be going next. And as it goes, you can see, it's keeping track of the voxel age. So even though it explores places, it's not getting too far away because things get out of date. So it has to go back and explore them again. And so this is just one behavior that we can look at as a way to understand, how this architecture can be used to operate. Okay, here's another scenario. This is a search and rescue scenario where we've changed the weights a little bit, and we've initialized the map with a target location to the south. So in the bottom of this map. We've said there's a person missing. We don't know exactly where he is, but we know he's to the south. And so you can see in the score map down on the bottom left, there's a lot of value, a lot of weight being given to everything on the bottom of that map, the south side of the map. And our target is always now to the south side. So it's moving now, instead of staying near the origin where it was before, it's moving to the south. And we're going to speed it up a little bit again here as it continues to explore. And it's going to keep going until it identifies a person. So that top image in the middle is the forward-facing camera, and it's running an object detection algorithm looking for a person. Now we're just simulating it here. We're not actually running it through an object detector, but we can simulate what it would be like if it were able to detect this person. And you can see after a while here, it's detected this person. And so it goes into a different mode where it's just going to now zoom in and keep an eye on that person so that a rescue team could come and reach that location. So this is another example of how we could adjust the behaviors to get, or adjust the weights and the preferences to get a different behavior profile for this drone. Okay, so in conclusion, there's a lot of benefits to using these simulated environments. They're really useful for developing testing AI algorithms. UAVs are great research platforms. Having the ground truth is really helpful for being able to evaluate the performance, and the modular design of all of this using ROS allows us to swap out different components to unit test each of these components individually. Using the voxel map is a great way to represent the agent knowledge, especially spatial knowledge. It's a way we can encode prior information into that voxel grid. For instance, search to the south. We can do more complex spatial reasoning things in the future, like understanding what that environment looks like. And it's just a really interesting testbed for path planning and multi-criteria problems. And so the multi-criteria stuff can be extended, of course. Lots of different application domains can be expressed within this framework. We can use it to explore the ideas of human-robot teaming a little bit, and try and figure out what features are important, and maybe even use it as a test bed for things like reinforcement learning to do some learning problems. So that's the talk. Thanks for your time. Thank you.